Hello, students! Today we are going to learn about a very common vision defect, one that some of you might even have. It's called myopia.
So, let's quickly look at the topics we will be covering in today's lesson. First, we'll talk about a blurry world. Then, what goes wrong inside, followed by why does myopia happen? After that, we'll discuss correcting the vision, tackle some exam numericals, and finally, we'll have a summary and final advice. This will help us understand the concept thoroughly.
Let's begin with a situation that some of you might have actually experienced personally. Imagine this. You're sitting in your class. You can read your textbook perfectly, every word is crystal clear. But when you look up at the blackboard, the words on it are just a blur. Does this sound familiar to anyone?
Well, this exact condition, where you can see nearby things clearly but distant objects appear blurry, is a vision defect. We call it myopia, or as it's more commonly known, nearsightedness.
Okay, so here is the formal definition, which is very important for you to remember for your exams. Myopia, or nearsightedness, is a condition where a person can see nearby objects clearly but cannot see distant objects distinctly. Please make a note of this.
Now for the really interesting part. Let us try to understand what is happening inside the eye that is causing this effect. What goes wrong that makes distant objects look so blurry?
Now, I want you to look at these two diagrams very carefully. The top diagram, this one here, shows a normal eye. You can see the light rays focusing perfectly on the retina at the back. Now look at the bottom one. This is a myopic eye. Can you see the difference in where the light is focusing?
Yes, that's the crucial point. For us to have clear vision, the image must form exactly on the retina. But in a myopic eye, the light rays from a distant object form an image in front of the retina. It doesn't reach the retina, it falls short. And because the image is not formed on the retina, what we see is a blurry picture.
Okay, so the next logical question is why? Why does the image form in front of the retina? Let us investigate the two main reasons behind this condition.
So there are two primary physical changes that can happen in the eye to cause myopia. The first one is the excessive curvature of the eye lens, and the second one is the elongation of the eyeball.
Let's break down what each of these causes means in simpler terms. First, let's talk about excessive curvature. This means the eye lens has become too curved, or you can say too thick. Now, a thicker, more curved lens bends light more strongly, right? It becomes too powerful. So it converges the light rays too much, and they meet in front of the retina. The second cause is an elongated eyeball. Here, the eyeball itself becomes longer from front to back. So even with a normal lens, the retina is now simply too far away. The light focuses where it should, but the retina isn't there to catch it. It has moved further back.
All right, now that we understand the problem and we know the causes, we can start to think about the solution. How do we correct this vision?
So think about it. The problem is that light is bending too much and focusing too early. Our challenge is to somehow move that image from in front of the retina back onto the retina. How can we do that? We need to reduce that excessive converging power. And the answer is we use a concave lens of an appropriate power. This diagram here illustrates how it works beautifully. You see, a concave lens is a diverging lens. Its job is to spread out the light rays a little bit before they enter the eye.
Let's follow the path of light step by step. First, the parallel light rays coming from a distant object hit the concave lens. What does the concave lens do? It diverges them. It spreads them out slightly. Now these already diverged rays enter the eye's natural lens. And finally, our eye lens, which was a bit too powerful, now converges this light perfectly onto the retina, forming a sharp, clear image. So the concave lens gives our eye a little bit of help.
Okay, now for a very important section for your exams, solving the numerical problems related to myopia. So please pay close attention as we understand the far point and lens power. First things first, we must understand a concept called the far point. What is it? The far point is the farthest point up to which a person can see objects clearly. Now, for a normal eye with no defects, the far point is at infinity. That means you can see the moon and the stars clearly. But in a myopic eye, the far point is much closer than infinity. It might be 2 meters, or 1 meter, or even 80 centimeters. This value, the far point, is the maximum distance a myopic person can see clearly. And this is the value that you will usually be given in your exam questions.
Please, I want you to note down these key rules for solving myopia numericals. They are the key. So what does the concave lens do? It creates a virtual image of a distant object, an object at infinity, and it forms this image at the myopic eye's far point. So for our calculations, the object distance, u, is always taken as infinity, and the image distance, v, is the person's far point, for example, minus 80 centimeters. And very importantly, because we are using a concave lens to correct myopia, the focal length f and the power p will always be negative. Remember this.
So, this brings us to a very simple conclusion. The focal length of the concave lens that is required for correction is equal to the distance of the far point from the eye. So if the far point is at 80 centimeters, the focal length of the lens needed will be minus 80 centimeters. It's that direct.
Okay, before we finish, let us quickly summarize the main points of our lesson today. This will be very useful for your revision.
So what have we learned today? First, myopia means you can see near objects, but not far objects. The cause? The image forms in front of the retina. What are the reasons for this? It's either a high curvature of the lens or a long eyeball. And how do we correct it? We use a concave lens. And finally, for numericals, remember that the power of the corrective lens for myopia is always negative.
And finally, here is my advice to all of you, especially for your board exams. Don't just learn the formulas separately. Always connect the ray diagram with the numericals. Try to see the physics happening. When you can visualize how the light rays are bending, the numbers will make perfect sense. Thank you.